Let's look at a maximization problem, sometimes called an optimization problem here. David has 80 yards of fencing to enclose a rectangular area. Find the dimensions of the rectangle that maximize the enclosed area. What is the maximum area? So anytime words like maximize or minimize are thrown about in a problem, that's referring to the relative max or the relative min concept that we discussed in an earlier topic, right? What's a relative max? Informally, we described it as the top of a hill, right? A function is increasing, it reaches a relative max, and then it begins to decrease, right? So this is a relative maximum point. So what they're essentially asking for when they say maximize the area, they're saying if we can create a function for area, and we'll call it a of x, right? Let's call this the area function based on the variable x. If I can create that function and find its maximum point, then I will have maximized the area, okay? When the problem is talking about a rectangular area, okay, use my fancy tools here. So when we label this, there's 80 yards of fencing, right? Now, I don't know any of these side lengths, right? But I'm going to call this X. And if that's X, then this is X as well. When it comes to labeling this, because we don't know anything, right? If you've done this in Algebra 1 or Algebra 2 where we were doing systems of equations, then it would be okay to label this as Y, okay? But our job, just to remember, just to rehash this, our job is to create a function to find the area of this rectangle that is strictly based on the variable x. So I don't want y variables involved here, right? So when you look at this, and we've used x twice to enclose just two sides of this, that means I don't want to call this x. I want to call this side length something, or excuse me, I don't want to call this y, right? I want to call this side length something based on x. So how could I express that? Well, if I've used x linear feet or yards, I should say, x linear yards for this piece and x linear yards for that piece, then at this point, I have 80 minus 2x linear yards available to enclose these two sides, right? Take away this x and this x from the 80 yards of fencing. This is how much we have left to cover the final two sides of the rectangle. So what would I call this one side length? One side length would take half of what we have left, right? So this represents the amount of fencing left after the first two sides. Take half of that, and that would represent the length of this side. Okay, so what does that look like? Well, I can't cancel this 2 with just this 2. I'd have to factor 2 away from the values in the numerator, then I could cancel it. So 40 minus x is a representation for this side length. Okay, so I don't have to use the question mark anymore. So now I know that this side length is 40 minus x. And because I have my side length here and my side length here, I know the area can be calculated by taking x, right? Length times width, x times 40 minus x. So this is a function based on x that I can graph in the coordinate plane now and try to find a maximum point for. All right. Now, sometimes your calculators, your TI Inspire calculator might not be able to handle this. It's best to distribute this x in. Sometimes we would not want to do that. In this case, we do. Okay. So here's our area formula, length times width in terms of x. Now take a look at this for a second and just pause, because if we're supposed to maximize something, that means there has to be a top of the hill, right? Now I drew this ahead of time. That means one possibility for the function is it's a parabola that opens down. Is this parabola going to open down? Yes, it is, because the leading coefficient of the squared term is negative. So we know that when we go to graph this, it's going to be a parabola that opens down. Okay, let's go and let's take a look at the graph itself. Okay, if I type this in, 40x minus x squared, no matter what graphing utility you use, you're going to have a hard time seeing this, right? Because we've got a small window. If we zoom out enough, if we're using Desmos, we start to see that there will be a top of the hill right here. Okay, so we see our relative maximum point at 20 and 400. Now it helps if you understand what's the 20 and what's the 400. Well, 20, that's the x coordinate, right? So, all right, we know that our max, the top of the hill, is at 20 comma 400. Okay, what's 20? This is x. This is that initial side length. Okay, a of x, also known as y, right? Our variable y is 400. So this is the area because the area is based on this independent value of x. And if this side length is 20, okay, let's change the colors here for a second. If this side length is 20, that means this side length is 20. And if x is 20, 40 minus 20 is also 20. So even though they said it's a rectangular area, what we do is we've actually created a square of side length 20. And 20 times 20 is at 400. So what is the maximum area? 400 square yards with a side length of 20 yards on each side.